Welcome to Ask and Learn.
Okay, so for this question we are given that j times 2n is equal to 2 times jn minus 1 when n is greater than or equal to 1, and that j 2n plus 1 is equal to 2 times jn plus 1 when n is greater than or equal to 1. And j of 1 is equal to 1. We want to prove, so the question is asking us to prove then that jn is equal to 2k plus 1, which is what we found in a previous exercise, when k is less than 2m and n is equal to 2m plus k. Okay, so we have our given above and what we are trying to prove. And this wants us to use induction specifically. So we'll start with our basis step, which is when n equals 1. Okay, so we'll note that one is equal to 2 to the power of 0, which is also equal to 2 to the power of 0 plus 0. So this is just getting it in this form, right? Okay, additionally, 2 times 0 plus 1 is equal to 0 plus 1 is equal to 1 is equal to j of 1. Okay, so if we're letting p n be j of n is equal to 2k plus 1, then we can see here that in that instance, p of 1 is equal to j of 1, right? So p of 1 is not equal to j of 1, but it holds true when we have things in this form here. Okay, so that was our base case. And then we want to move on to our induction step. Okay, so induction step. Let's assume that P1 all the way through PR is true. Then we need to prove, so need that the case of P Q plus 1 is also true. Okay, so this is actually going to be broken down into first cases. So case 1, is that Q is odd. Okay, in that case, it follows that Q plus 1 is even. And if Q plus 1 is even, then there exists some integer r such that, so do st for such that Q plus 1 is equal to 2r. Okay, so if that's the case, and if Q plus 1 is equal to some value in the form of 2 to the power of m plus k, then r is going to be equal to some value of 2 to the m minus 1 plus k over 2. Okay, so we just use the relationship above to derive that. And so if that's the case, then we can consider j of q plus 1, which is equal to j of 2r, which is going to be equal to 2 times j of r minus 1, which was given to us just by the formula up here. And so that's going to be equal to 2 times k over 2 plus 1 minus 1, okay, which is going to be equal to 2 times k plus 1 minus 1, which is also just equal to 2 times k plus 1. Okay, so therefore, we know that p to the q plus 1 is true for when q is odd. That was only half the cases, right? So now we need to consider case 2, where q is even. So if q is even, then it follows that q plus 1 is odd. Right? And so if that's the case, and there exists some integer r such that q is equal to 2r. And then we'll follow similarly to above. So, or the previous pages, I should say. So if q plus 1 is equal to 2 to the power of m plus k, then q is going to be equal to 2 to the power of m plus k minus 1. And r will then be equal to 2 to the power of m minus 1 plus k minus 1 over 2. And that stems from this relationship here. Okay, so we're going to use that to derive j of q plus 1, right, which is going to be equal to j of 2r plus 1, which in turn is equal to 2 times j of r plus 1. And that, again, comes from the formulas given to us initially here. Okay, and so then we can break this down. So this is going to be equal to 2 times k minus 1 over 2 plus 1 plus 1, which is equal to 2 to the k plus 1. And so again, this holds, right? So here we have p of q plus 1 is true when q is even. And since it holds when q is both even and odd, then by induction, p of n is true for all positive integers n. Okay, so that concludes the proof. And do note that I didn't write down everything, right? So I didn't write that this must be a positive integer, but those are important details.